online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope here at the David Dunlap Observatory. Together with RASC volunteer Rohan Kwan, I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you are joining us from. This helps us make sure that our technology is working properly. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the DDO, the David Dunlap Observatory. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are happy to bring you virtual programs like this instead. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Dr. Josh Speagle. Josh obtained his BA in astrophysics and physics at Harvard University in 2015. After spending a year abroad at the Kavli Institute for the Physics and Mathematics of the Universe at the University of Tokyo, he returned to Harvard, where he obtained his MA and PhD in astronomy in 2020. He is currently a Banting and Dunlap postdoctoral fellow at the University of Toronto. His research focuses on trying to understand how galaxies, like our own Milky Way, form, behave, and evolve by studying data from billions of stars within our own galaxy, as well as data from billions of other galaxies. Tonight, Dr. Speagle will discuss mapping our Milky Way galaxy and explain some recent advances in how we understand our place in our home galaxy. If you have any questions for our speaker, please post them in the YouTube chat. Dr. Speagle will have time to take your questions at the end of his talk. Please join me in welcoming Dr. Josh Speagle.
Thanks so much for the wonderful introduction. It's so great to get a chance to talk to everyone and hopefully get a chance to meet all of you virtually. And I'm really excited to have the opportunity today to talk a little bit about some of the work that both me and, as you can see here, lots of collaborators, both in Canada as well as across the world, have been working on really trying to understand and map out our own Milky Way galaxy. If you have any questions, in addition to asking them in the chat, you can also feel free to contact me. My email is j.speagle@utoronto.ca. So feel free to send me an email, and I'm happy to answer it afterwards. So one thing I want to open up with for this talk is to ask a question: what really is the Milky Way? We hear the term a lot, and I think there are two different ways that we think about it. But I think the most obvious one is from the perspective of what we as humans saw when we went outside and looked up at the night sky, which is we see something like this. We see this night sky filled with stars and planets and all these other phenomena, and we saw this band of sort of bright and dark features that sort of cut across the night sky. And cultures for millennia have constructed lots of stories and legends about what exactly these types of things mean. Is this some river? Is this the spine that holds up the sky? And that sort of thing is what we, have referred to as the Milky Way. What we understand today is that the Milky Way is really this galaxy that encompasses most of the stars that we see in the night sky. And so we're really living in this galaxy ourselves. This is kind of the most exciting picture I like to think of the galaxy. This was attained with the Gaia satellite. which was launched just a few years ago, and has been collecting data on over 1 billion stars that we can see. And so this is an all sky image, and almost every single little dot and fleck of light you can see on the screen is the galaxy. So this is all stuff that we see. And you can also see two of our closest neighbors, in this case, M31 or Andromeda. And so this is kind of the thing that I really want to study, is to understand, this is kind of what we see when we look out at the night sky. But what does this actually look like? We can't actually tell because we're kind of embedded inside the galaxy ourselves. It's one of the reasons why when cartographers went and mapped out the Earth for the first time, we didn't really have this picture, this coherent picture of kind of what our entire planet looked like until we went up to space. But we do have the benefit that we can look out at other galaxies and use those to offer insights. So when we look out, for example, at galaxies like M101, we can see these beautiful spiral structures, these dark lanes of dust, this central region, all these different colors, which indicate things like star formation. We can see these bar features in the center. We can see, we look at galaxies edge-on, we can see merging effects. All these different types and diversities of galaxies give us some insight into what we think our own galaxy might look like. And using those, this is kind of the best state-of-the-art picture that we've come up with. And so I want to emphasize that this is an artist's conception, because unfortunately, we think we're here, but we can't really leave our own galaxy and kind of look at it from the outside to get this type of, overview snapshot. So this is really a reconstruction from all the best data that we have today of what we think our own galaxy looks like. Again, based on lots of insights from other galaxies, plus some other data from our own. And I'll actually show you through this talk exactly how, the state-of-the-art data that we use to make some of these pictures. So one of the challenges that I'm really interested in, and lots of other astronomers around the world really want to know, is how do we go from this picture on the left, where we're looking out at the night sky and we see all these different stars and this band of light and darkness, and how do we take that and turn it into a 3D map of our own galaxy? And this is exciting, both, I think, because it's really cool to actually be able to map out the universe. But there are also, I think, 3 core ideas for why, understanding sort of our place in our own galaxy really matters. The first is our origins. Understanding what our own galaxy, the Milky Way, looks like today tells us a lot about how we got here and also our place in the universe. We can figure out where the sun might have been born, how it's migrated over time, and how lots of planets have maybe moved around throughout the galaxy, and the origins of life. That's also really important when we want to search. If we want to know where to look, we want to know where all the stars are. We want to understand how they've evolved, how they behave. These are crucial ingredients for understanding where life came from. And finally, galaxies are also really cool from a fundamental physics perspective. One of the first sort of key insights into things like dark matter actually came from looking at the behavior of our own galaxy and nearby galaxies. And so by trying to understand structure and dynamics, the movement of stars and gas and dark matter can help provide clues to some of these unanswered questions, like what makes up, the majority of the matter in our universe that we still don't really know today. That's unlike anything that we sort of have a lot of experience with. So in this talk, I sort of break it down into 4 parts, although we're going to skip over one of them. What I want to highlight first is kind of the history and background of what sort of people have done to try and understand and construct these types of maps of our own galaxy, and what sort of ingredients do we need to get there. I'll skip over part 2, which goes into a little bit more of the mathy side of inferring sort of these different properties. And then I'll jump straight to sort of some of the cool results, which is how, our understanding of the galaxy has really been revolutionized, both, nearby, close to the sun, as well as at large in recent years, based on these wonderful new data sets that have come online, plus sort of the advent of large-scale computing and more sophisticated methods to understand what lots of stars are doing. So mapping out the Milky Way has quite an illustrious history. In fact, the first map was constructed all the way back in 1781 by William Herschel, and was published in one of his books on the construction of the heavens in 1785. And what you see there is actually directly on the right. This is the map of the Milky Way that Herschel constructed. And of course, the sun is at the center of this conception of the Milky Way. So Herschel thought the sun was here, and all these other stars kind of go out. And so we know this isn't quite right, but it actually gets quite a lot of features about the galaxy correct. We see it has kind of this pancake shape. There seems to be this asymmetry where there are more stars off to kind of the side and fewer sort of up or down when we look away from the sun. There also seems to be this effect where we look in one direction, there's a lot more stars here on the right, except for this chunk that's kind of missing in the middle, and there are a lot fewer sort of out here on the left. And we understand now where lots of those come from, and understanding how exactly Herschel went about constructing this map, which was revolutionary at the time, and why it kind of has some features that are right and some features that are wrong, connects really deeply to our quest to map out the galaxy today. So how did Herschel do it? Fundamentally, the idea was if you look out the night sky, you can just go up and actually count all the stars. So if you go to a given region and you see if there are some stars here and some stars elsewhere, you just see which stars are brighter, which stars are fainter, how many stars there are. You just kind of map them out. And if you make two key assumptions, you can turn sort of this two-dimensional image of the sky that all of us see every day into a three-dimensional map. The first is that all stars have the same intrinsic brightness. That means that, similar to a light bulb that you might plug in, which has, a certain types of light bulbs have the same brightness. If you see a star that's a little fainter, that's because it's further away. And so all these stars, the bright ones and the faint ones, all have the same brightness. And so if they're fainter, they're further. If they're brighter, if they're closer. The second is that there's no real material between us and other stars. If you look at these dark patches, that's just because there are fewer stars there. So you can use that to directly trace out the shape and structure of the galaxy. The first assumption comes down to this idea that the brightness that we observe is related to the intrinsic brightness divided by the distance squared. This is known as the inverse square law. As things go further away, then they get fainter. The second is related to this idea that the density, which I have referred here to the Greek character rho that we observe, is the same as the actual true density that we think exists. So these dark regions really do correspond to a lack of stars. And it turns out that both of these assumptions are wrong, but the way that they're wrong is actually quite interesting and helps us a lot with our quest to try and construct better maps of the galaxy today. So I'm going to focus on each of those in turn because they each connect to different parts of what makes our own galaxy and the law of astronomy really, really interesting. So the first is the idea that all stars have the same intrinsic brightness. It turns out that this isn't quite true. Measurements of the intrinsic brightness and colors of stars, led by Hertzsprung and Russell, two scientists in 1910, show that actually stars have a wide range of values. In other words, some stars are really bright, some stars are really faint. And that turns out to correlate with a color of a star. Bluer stars tend to be brighter than redder stars. One way to visualize this is a plot that's shown on the right. The color here shows the relative density of stars. The y-axis is the brightness. So brighter stars are kind of up here, and fainter stars are lower. The x-axis shows the color. So bluer stars are on the left, and redder stars are on the right. What you can see overall is there's this correlation where as stars get brighter, they tend to get bluer, and as stars get fainter, they tend to get redder. And this behavior often has stars classified into different types. For example, some stars are called these main sequence stars, which we know now is where stars spend a majority of their lifetimes. Then there's this giant branch, which is what happens when stars use up all of the fuel that they're using to kind of can produce energy and then expand to be these big red giants. And then finally, some stars kind of end their lives down here. These is sort of a region called white dwarfs. But the key thing is that there is a correlation here. So not all stars have the same brightness. They do have different brightnesses. But we know that for stars that are fainter, they're redder, and stars that are brighter, they're bluer. So we can still use some of that information to get distances out. One of the other ways that we can get distances besides sort of looking at the brightnesses and colors of stars is actually this cool trick called parallax, which is the fact that when you look at an object from two different perspectives, it actually looks like it's in a slightly different place. So just to highlight what that looks like, if you're, say, here in viewpoint A and you're looking at a star and there are these different colored backgrounds, in this case, red, white, and blue, if you're from viewpoint A and you're looking at the star kind of diagonally, you're going to see the star sort of relative to the blue background. Versus if you're over here from viewpoint B, you're going to see it relative to the red background. This is something that we actually use all the time, and one of the reasons why we have two eyes. And actually, if you cover sort of one eye versus the other, you can actually see kind of this effect in practice. If you look at something close by, it'll actually shift because you're looking at it from a slightly different angle. So this helps us because it turns out that luckily for us, the Earth actually moves throughout the course of the year. It orbits the sun. And so that means we can use this really cool trick where if we look at stars that are close by from one side of the orbit and we wait 6 months and we observe from the other side, where it looks like relative to the background set of stars that are much further away will actually be slightly different. So the line of sight we see in January versus what we see in July will actually have slightly different positions. And we can use this to get independent measurements of distance. In fact, what you can show is for most stars, essentially, this is just equal to 1 over this little symbol here, which is the actual parallax that we're able to measure. So this is great because this means that if we now can go and observe a bunch of stars and we can measure this sort of effect when the Earth is on one side of the sun versus the other, we can get distances to them, we can see what they look like, and we can use that to actually go out and infer the intrinsic brightnesses of other stars. And that sort of is how we get this, diagram over here. And lots of the work that's been done since then is having to go out, get distances to these stars, figure out how bright they are, figure out what color they have, and use that to learn about all of this. So this took hundreds of years and the effort of many, many generations of astronomers to sort of arrive at our understanding today. And so this is now the state of the art that we're able to measure, at least courtesy of about 2016 and 2018. So what this means is that let's say that we have an unknown star. Let's say it's down here. So we observe its brightness to be, here, and it has this color. We don't know its distance, but what we can do is we can say, well, why don't we just compare it to stars that have similar colors? So we take stars that are also kind of, in this case, maybe yellowish, and say, what are the brightnesses of those stars? And we get a little region like this. And that means that since we know kind of how bright that star is, since we know it, we're comparing it to other stars that are sort of a similar color, yellow, then boom, we can get a measured distance out. And so this is sort of the first part of what Herschel tried to do was assume that all these were the same. And while they're not quite the same that we know now, we at least are able to do, somewhat the same type of thing. The second challenge turns out to be a little bit harder, which is the assumption that there's no material between us and the stars. It turns out that space is actually not totally empty. There's stuff there. And that stuff is something that we refer to as the interstellar medium. And it's filled with gas and dust and all these other materials that are formed, from stars, from these supernova explosions, from sort of the Big Bang. And it's now just kind of floating around in space. There's not a lot of it, but there's enough that it really matters. In particular, dust, or cosmic dust, is only about 1% of this interstellar medium by mass. So most of it are things like gas. But dust actually, similar to dust on Earth, it blocks stuff. And in particular, it scatters about 30% of all the light. So all the light that's emitted by stars will get blocked by dust and kind of pushed off in different directions. And so we don't see that. What's shown here on the bottom is actually a sky map of dust that was constructed with the Planck satellite about 10 years ago. So the color scale shows the amount of dust. So black means more and white means less. And the x-axis here is in these weird units of galactic coordinates. So this longitude is kind of like if you spun around sort of in the plane of the Milky Way galaxy. And when you look up and down, that's essentially when you're looking up and down sort of relative to the center of the Milky Way. And so that's why you see a lot of dust kind of gathered here in the center, in this central region of the galaxy here. You see a lot sort of towards the galactic center, which is located at 0. And at the edges, this is sort of looking away from the galactic center, looking towards the outskirts. What you could just see here is that there's not just a lot of dust measured in, measured this way, but it has all this really interesting structure. We see all these interesting loops and filaments and weird eddies and swirls. And these are all remnants of things that have happened in the past, of supernova that have gone off on interesting channels of magnetic fields that tell us a lot about our own galaxy. But for our purposes, they kind of get in the way, which is that because they block a lot of the light from stars, And that can make it a little hard to tell sort of what the star actually truly looks like. And that's because of two effects known as extinction and reddening. Extinction is the fact that dust is just going to block some light. It's going to scatter it away from us, so we don't see anything. So this image on the left is actually looking at a bunch of stars in the optical, sort of the wavelengths that we're used to seeing. What you can see is that we don't see anything in the center. That's because there's a big cloud of dust in the way. The other effect is called reddening, and that's the fact that because of the size of the dust grains, they tend to do better at blocking light that's bluer, that has shorter wavelengths than light that's redder. And so therefore, when you get closer and you have more dust, the stars look redder. That also means if you look sort of in the infrared, you can actually see through the dust. Although again, like the stars all look kind of redder than the outside because dust has affected their color. So what this effect means is that our previous case, where if we observe a star that has, say, kind of a yellowish color, and we say, boom, we kind of know what stars we can compare it to. Once you incorporate the impact of dust, this gets a lot more difficult. You suddenly have a whole range of possible values that a star could be. In other words, let's consider two extremes. Maybe the star is kind of red because it really is red. Therefore, there's not a lot of reddening. There's very little dust, and it's very close by. It's a faint red star. Or maybe it actually is kind of yellowish or blue. Maybe that means that it's a brighter star that's further away with more dust in front of it. And the dust is going to have this effect of making it redder and making it appear dimmer. And there's also this third thing. You'll notice, again, I mentioned this giant branch, which is up here. And so this in astronomy is often called this uncertainty between whether a star is a dwarf, which we refer to as stars like our sun that are kind of relatively small, versus stars that have gone through this red giant phase, like Betelgeuse, which should explode any time now, plus minus 10,000 years. So these types of uncertainties then make this problem pretty difficult because we don't know whether when we see something that's red and faint, whether it's close by and actually, that particular color or brightness, or whether it's really far away and it's just a lot of dust in front of us. So this is kind of what the result looks like. So using a lot of different statistical techniques, what we can do is we can infer kind of our best guess for the distance to a star and the amount of dust in front of it. And so each panel here shows essentially the best guess to a bunch of stars towards a particular region known as Orion, which I'll show in a few slides. So this red cross is our best guess. The x-axis is kind of some measurement of distance, and the y-axis is some measurement of the dust. And the blue region shows kind of our uncertainty around it, all the possible solutions that are kind of consistent with the data that we see with the images. And so in some cases, we get this really good estimate that the star is close by, so shown here on the bottom, and kind of doesn't have a lot of dust. But in some cases, we have a lot of uncertainty. We sometimes don't know if the star is close by here. Maybe sometimes the star could have multiple, possible locations. And this all comes back to this uncertainty we talked about before. And trying to really get a handle on this has been one of the things that my research is focused on with all the collaborators, so we can construct sort of these types of estimates. In the past, though, this has been much more difficult. So what a lot of astronomers have tried to do is to get around this work by focusing on these things called masers. And what masers are, they're short for microwave lasers. And so it turns out that they're in these really, really dense regions where new stars are being born. You get this really cool physics that happens that causes essentially these beamed microwaves to just like shoot at us. And we can detect them with really, really good precision. And so these are really bright in radio wavelengths. And that means we can get really precise parallax measurements. And that means distances to these things without worrying about the dust. Example is sort of shown here on the right. This is a star-forming region. You can see the dust kind of all highlighted here. We have some stars kind of at various places. And this maser is in this really dark region where we have all of this dust where new stars are being born. The challenge is that this is really, really time consuming. To do a single maser observation, you require tens of hours of observing time that you really need to just get a distance to one particular source. So what it means is that right now, sort of, the state of the art is that we've measured distances to about 150 or so masers. And that data set is shown here on the right. So this is now a view of our galaxy from the top down. So the galaxy, sort of this cross here is the center. Each of the different colors shows a different model that's being fit to the data for spiral arms. And these different points, those all show the actual positions of the masers that we're able to measure. And you might look at this and say, this looks a little familiar to something I maybe have seen before. And you'd be right. If you look at this artist conception that we have, this is the data that it's based on. And if you flip back and forth, you can actually see that correspondence. The arms that we estimate, the shape and size of the galaxy is based essentially on these measurements of about 150 objects. So this is kind of where our science is. And the question is, what can we now do to kind of really build off of this based on these really new exciting data sets to really revolutionize the understanding we have of what our galaxy looks like and how it's behaving. So one of the things that I'll show now is what we can do when we move from sort of 150 objects to now thinking about millions and hopefully billions of stars that we can use to build up these types of maps. So one of the ways that we can scale up is that we want to get away from using these types of really rare objects. Masers are super cool, but they're not that common. They require really special conditions to actually occur, and they're really, really time consuming to observe. But as many of you probably know, when you look out the night sky, you can just see stars everywhere. Even in this image, there's thousands of stars that we can see, but only one maser, which is just here at the center. They're super common. We can get pictures of them, really, really cheaply and really, really quickly. We have data on billions of stars, and we have tons of really cool computing power now. And so that means we can now think about using lots of these stars to do really, really cool science. And I'm going to skip over exactly the details of how that works and jump straight to the really exciting results. So I want to focus on two regions. First, thinking about things right around the sun and how all this stuff has really changed our understanding of where we come from, and then thinking about moving to the galaxy at large. One of the reasons that trying to think about the galaxy around the sun is really important is we want to understand our little solar neighborhood. You want to understand how our star came to be. And what we know is that when we look at things like the Orion Nebula, a picture of which is shown on the right, this is something you can observe. It's sort of right under Orion's belt if you're looking at the constellation. This is actually a really dense cloud of molecular hydrogen gas. And stars are kind of born out of these really dense clouds, which are traced really, really well by dust. And if we can study them and understand, where their structure is, where they're located, we can try and figure out kind of how stars like our sun might have been born. What are the conditions for which it formed? How did we get our asteroids? How might we have gotten water? All these things like that. And so the problem, of course, is that it's really difficult to determine accurate sizes and masses to these things without distances or 3D geometry. Again, we can see this cool picture, but we don't really know how big it is or how far away it is. And that means it's difficult to say kind of what the real scope or extent or properties of these types of star-forming, giant complexes are. And so this is kind of the cool part where what used to be sort of a drawback can become a strength, which is that if we think about what's going on in the interstellar medium, we have these stars that are kind of distributed all throughout space. And they're kind of, we observe them as they're kind of moving through this field of dust and gas. And that's going to affect their brightness. So stars that have the same sort of colors are going to now have things that are redder, and some of them will be affected less. And so for an individual star, this is not great because it means that there's some uncertainty. But if we think about having many, many stars, this really blurry picture can become really clear. In other words, we can actually use stars to map out the distance and the distribution of dust. And by using dust, we can then trace things like spiral arms or these types of clouds and understand, where exactly they are. So this was a really fun project that I did in collaboration with Catherine Zucker at Harvard, along with several other collaborators. And our idea was essentially as follows. If we look at a given region of the sky, which is shown here, the colors are a little flipped, so more dust is kind of in white. What we wanted to do is we wanted to take, say a little circle and put it down and say, what is the properties of dust in this little region going to look like? And this is kind of the model that we came up with. If we think about cumulative dust, which is kind of this y-axis, so essentially as you get further away, you're going to get more and more dust because you can't have negative dust in front of us. This x-axis is going to be distance. So there's going to be some stars kind of hanging around in front of this, big cloud where all these stars are being formed. Then boom, we're going to hit this giant cloud. It's going to have a ton of dust. And then afterwards, we're going to have some stars that are kind of hanging out behind the cloud. And these all have different types of uncertainties. So we're going to add in some additional stuff, and maybe we get things wrong sometimes. So we're going to have a little bit of modeling to account for this too. And so what's really cool is that this type of project, where you're trying to get these distances out and change masers, have really been uniquely enabled by a lot of advances in modern technology. These big data sets, working with a billion stars across the whole sky, using new tools such as the ones that my collaborators and I are developing, and then using that to derive sort of these estimates that I showed you before. And when we combine them into this model, we can get some really, really cool results. I don't have enough time to sort of show you all these things in detail, but one of the things that my collaborators and I love to do is to make interactive figures. So when you follow the link, for example, that I've highlighted here, what you can do is actually explore all of our data yourself, sort of in real time, by mousing over and seeing exactly how things work and what stuff looks like. And here's kind of just a highlight of one of the really cool results that you can do with this. On the left is a cloud. This is a cloud called Cepheus, which has been widely studied. You can see on the left is just kind of this two-dimensional map of dust. So this is just showing essentially how much dust we think is there based on this Planck satellite, and it kind of just looks like this big blob. On the right shows the same thing, but now where these different colors indicate how far away we think different portions of this cloud really are. And one of the amazing things that we can see just from this is that by using stars, this region on the left actually is really two clouds that are right next to each other. They're superimposed on the sky, and we can separate them out and see that actually we have one that's further away and one that's closer. And we're just kind of seeing them both at the same time. That's something that's very difficult to do when we're just looking at the data on the left, but when we use sort of these millions of stars, we can start to gain these really, really cool insights. We also do really well when we compare our results, which are on the x-axis, using all of these stars, and we are comparing to these really high quality masers, these super rare objects, we get super good agreement. And so essentially our method allows us to just take any sort of image of the sky and apply our method and get distances out that look like they're just as good as these super expensive, really rare objects that people have been using for decades. One of the things that we've been able to do is actually construct really detailed maps of the solar neighborhood. So this is what I'm showing here. This is a top-down view of the sun, which is kind of highlighted here in yellow. And each of the different grayscale on the bottom kind of shows the distribution of dust, and all of these individual sort of blue regions are places where we've mapped out different star-forming regions around the sun. And we have a little zoom in so you can see in detail kind of all these things labeled and what sort of their properties are. This small thing here is called the local bubble. The fact that actually sort of around the sun, there doesn't seem to be a lot of star formation happening or a lot of dust or gas. So something seems to have driven a lot of this out. But once you go a little further, you then see there's all this kind of dust here in all these different regions, all of which are forming stars. And so we've been able to really benchmark sort of where lots of those are based. And one of the things that came about from doing this that people had not seen before is that there's just this humongous line that kind of goes from the top left up here down to the bottom that nobody had seen before and seemed to coincide with kind of our understanding of our local spiral arm that we think the sun is based in. And so we called this structure the Radcliffe wave, based off of the Radcliffe Institute at Harvard, where this was first discovered. And again, I can't go through the details of showing you a really fun interactive figure here for the purposes of time, but if you follow the link and click on this, you can actually see this 3D model that we've constructed. But here's sort of a still shot where we've highlighted this particular region here in red. And this is super cool because by deriving these new distances to all these things, we found this super long structure. It's kind of this undulating filament in all these different, this is sort of a side view. This is an end-on view that is over 2 kiloparsecs long. In other words, over 6 light years. That seems to, as far as we can tell, comprise more than 60% of the mass in what we used to think was our local arm, sort of where the sun is embedded. We don't really know what causes this type of structure to emerge, and we've been trying to really actively study it. but it overturns this paradigm that's defined sort of our understanding of star formation around the sun for about 150 years, which was known as Gould's belt, which really was based on the fact that this sort of region here seemed to be a circle. But once you saw that actually this, these regions actually connect up in this really, really long extended structure, we've been really trying to scratch our heads and figure out, what exactly this means about where the sun came from and how exactly our galaxy behaves on really small scales. So that's really exciting because this is something where, astronomers never ordered this. We weren't really looking for it. It's one of these really serendipitous discoveries that only emerged by constructing these types of 3D maps. And so we're trying to see how much we can learn about our galaxy from this type of finding. The final thing I want to end on is trying to look at mapping the galaxy at large. And this is kind of where I'll show, I think, the one and only and coolest sort of interactive figure to kind of explore lots of this big data. So what I've been showing so far is kind of this project to really use these star-forming regions, these molecular clouds, to map out things pretty nearby to the sun. And using that, we've discovered sort of some interesting things we didn't expect about sort of this spiral arm that our sun's embedded in, and maybe the history of how stars like the sun have been born. But what's more exciting is we can think about just getting every star that we can see on the sky and trying to construct a map of all of them rather than just a handful of the dust. And so this was something that we called Augustus, based on our Brutus code. And this was a trial run of about 170 million objects that took about 700,000 CPU hours. And so there's a little bit of technical details on the left if there are any astronomers in the audience. But the right sort of shows this map of where our stars are located, again, in sort of these galactic coordinates. So the Milky Way plane kind of cuts through the center. And if we look up and down, this is sort of looking up and down relative to the plane of the galaxy. This region here that we're missing, this is the south. Since the telescope we were using for this data primarily came from Hawaii, and unfortunately we can't see through the Earth as much as astronomers would love to do that. What's really exciting is that we can use this to actually try and visualize in sort of a very intuitive way lots of properties of our galaxy in ways that I think are really, really easy to show to lots of members of the public, as well as to improve our own understanding of detailed galaxy assembly. So one way to do that is we can think about taking a little slice. So in 2D, this kind of looks kind of like a donut. But if you imagine in 3D, this would be like taking kind of a little shell, like the outer layer of, say, an orange, and just seeing kind of what the properties are along the shell. And if we do that and we project it the same way as before, we get something that looks like this. And so the color here sort of shows the overall density of stars in this shell as a function of position in the galaxy. As we go, if you kind of zoom in, what you'll see also is that there are lots of little arrows everywhere on this diagram too, since we can also measure how the stars are moving. What you can see just by looking at this is there's this really clear structure where stars seem to be orbiting in this disk, where stars that are up here at the top seem to be following some different behavior. And this is sort of a really clear demonstration that there are multiple structures in our galaxy. There's kind of this flat pancake that we call the disk, and there's this kind of spherical component where stars are moving a little bit more randomly that we call the halo. If you look a little further out, we can now start to see something really cool. So at this point now, we have a map where we can see both the center of the galaxy, kind of near 0, and we can also see these outskirts really far away from the center, and this is around negative 180. If you look now at this, what you can see is that the galactic center kind of shows up really clearly as this humongous overdensity of stars. So there's a bunch of stuff happening in the galactic center. Unfortunately, we kind of cut that out in this plot, but we can see a lot of that. But what's really cool is if you look in the outskirts, when you look at sort of this outer region, way out here, we actually see this flaring effect where a lot of stars actually seem to be on much bigger orbits, kind of where the galaxy, rather than getting thinner as you go further away, kind of flares up in this really big structure. And we can see this really clearly when we look at the velocities of these stars. So if we actually measure how quickly these stars are moving, we can see that not only are they kind of moving in really, really similar patterns, but also at very similar speeds. And so this implies that all of these stars are kind of orbiting in this really, really fat kind of pancake as we get further away. So it kind of gets thinner, and then suddenly it gets a lot fatter when we go really far away. And this flaring effect tells us a lot about how our galaxy has evolved over time. I think these 2D images are a little limited. So what I want to show now is sort of a visualization that's based on maps of the Earth, in particular this one from Null School called All Sky, which tries to visualize the bulk flow of stellar motions in and around the sun. So what I'm showing here in this particular demonstration is actually the same thing I showed before. You can think of this like a map of ocean currents. So showing how the bulk motion of stars kind of changes as we look in different places on the sky. One reason I love this type of demonstration is you can click on various regions and see, where you're located, how quickly stars are moving, what direction they're located in. You can see, for example, there are these particular hotspots. These often correspond to particular structures like clusters of stars that we know. But what's really exciting is that we've enabled essentially the ability to actually visualize these in what I consider the most natural representation on the surface of a sphere. So we can actually kind of look around at this given little distance slice here and see firsthand what all the stars are doing as we rotate to various places on the surface of this globe, which we can think of as this slice in space. You can switch it up. You can see, for example, here's what we think the best chemical compositions are for these stars, measured in sort of iron content. We can see estimates for stellar ages and how they might vary in various places. So stars kind of closer to the plane are younger than stars that are further away, as well as overall density. And you can see, for example, here, the imprint of lots of these different dust structures I showed earlier, which kind of block out various stars from our sample. What's really cool is if you look further away, so this is now looking almost 13 to 25 kiloparsecs away, so over 40 light years, more or less, 40 to 70 light years. What you'll see is this feature that runs through this south here, and this whole thing, which you can see super coherently, shows up on this globe, but is very hard to visualize otherwise. This is actually a dwarf galaxy known as Sagittarius that has crashed into the Milky Way at least once. It's kind of been stripped of stars in this stream, and we can see it sort of swinging around the galaxy, sort of through the bottom, and then coming back through on the top over here in this type of visualization. So that's one of the really, really exciting things about being able to do these this way. This website is public, by the way, so you all are also welcome to follow the link and check it out for yourself. It's not perfect, but I think it is a really exciting way to visualize kind of all these different things. On the flip side, if we decide to look really closely, sort of just around the sun, you see structures that look like this instead. And so what might be going on here? Well, what this is showing is that when we're looking at stars that are just next to us, we're essentially looking at all the stars that are in the disk. And so either if stars are orbiting just like us and they're right next to us, we don't actually see them moving. And so that's what we see here are stars that don't really appear to be moving. So they seem to be converging towards the same point. They're kind of standing still, just like two cars in a highway. They're not, you don't really seem to see them moving all that quickly. But if you look kind of above, you'll see all these stars that are streaming past us. And so you can see that effect here as well. And so this is, I think, just a really great tool that we're really, really proud of to be able to look around, see all these different things, and be able to investigate lots of these effects for yourself. One of our really exciting goals for the future is to hopefully make this a fully immersive sort of 3D augmented reality experience. You can actually swim through and see all the stars sort of in real time rather than just in these little individual slices. So that's kind of where we're at right now. So kind of the state of the art is we're really trying to build up this picture of the Milky Way. And we're trying to use hundreds of millions of stars to make that happen. This builds on this legacy that stretches back hundreds of years, all the way back from Herschel, from this sort of first map. Involves a lot of modern day computing and statistics to actually get all of this done using hundreds of millions of stars. And then with that, we've discovered tons of new stuff about, the area right around the sun that hopefully will tell us more about, how stars like the sun have formed and how our local spiral arm behaves. And finally, we're starting to just scratch the surface of really mapping out the galaxy at large. And so hopefully in the future, we'll be able to build on lots of this. We're really excited that hopefully we're going to increase our sample by a factor of 10, and we'll be looking at 1.5 billion stars. They're just 170 million stars. And develop even better ways to try and visualize and map out this data so we can really construct kind of this, cartography of our own galaxy. And so that's kind of where I want to end, is just a lot of excitement looking towards the future. And hopefully, this was something that you guys also think is super fun. So I'm happy to take any and all questions. Thanks.
Thank you so much, Josh, for sharing this incredible look at the Milky Way. We're going to check in now with RASC member Rohan Kwan, who has been monitoring the YouTube chat for questions. Rohan?
Yeah, hi. Thanks, Denise. Good evening, everybody. As you may know, my name is Rohan. I hope everybody is enjoying the presentation so far. If you have any questions at the moment, you can feel free to post them in the chat, and I'll read them out for our speaker. But we have a few questions at the moment. So our first question is, how will the James Webb Space Telescope affect the mapping of the galaxy?
That's an excellent question. So James Webb is a very different type of instrument. So the galaxy or the telescope actually has a very small field of view. So it's not really great at doing like surveying the whole sky. What it is really good at doing is being able to get really, really good data on certain types of stars to improve lots of our models for how we think these stars kind of behave, and then incorporate that information into these maps that we're building. So one of the things that people are very excited about for James Webb is actually to go out and look at stars both in our own galaxy, but also in Andromeda, and compare the properties of the two and use those to better understand the physics of stellar evolution that we can feed back in to building these sort of beautiful results. So
Okay.
we're very excited that it will be launching in hopefully 2 months.
Yeah, I heard. That's very cool. I'm very excited as well. All right. The next question has two parts to it, but I'll start with a part one. As you and your colleagues have been looking at new ways to determine distances to other objects near to our solar system and in the larger Milky Way, have you found that previous distance estimates have been mostly correct, or are there some earlier estimates that you found to be widely wrong?
That's an excellent question. So it's a little bit of both. Most of the time, the estimates that we found have been relatively consistent with past work. One of the big challenges, though, has been many previous approaches have had really large uncertainties, and also sometimes have not been fully consistent with each other, since they're using a bunch of different tools and techniques and lots of different assumptions. But we found that overall our estimates have been very consistent with them and much more precise. There are specific cases, though, where we have found that our estimates disagree with sort of past results. For instance, there's this North Polar Spur object where a student actually derived distance estimates to this structure and found out that it was, much more likely to be associated with local structure rather than with something that was kind of a galactic scale, humongous thing that was very far away. So most of the time we're quite consistent, but sometimes we do find that the previous estimates have been wrong.
Yeah, okay. Yeah. And then the follow-up question is, how is this changing how we understand our place in the galaxy?
So that's an excellent question. I think one of the most fascinating findings has been the realization, actually, that a lot of stars in the galaxies have migrated quite a bit from where they're originally born. So, our sun is orbiting the galaxy many times throughout its life, but what we found is that because of a lot of interesting things about galaxy evolution, that turns out spiral arms probably don't stick around for a super long time. They kind of come and go and change shape. That actually ends up pushing a lot of stars around far away from where they were born. And so actually we think the star has actually migrated quite a bit ways out of where it was originally born, about 3 kiloparsecs, or sort of 10 light years or so.
Yeah, that's great. That's great. I don't see any more questions in the chat. So if you have any questions, feel free, don't hesitate.
Okay, thank you, Rohan. for relaying all of those great questions from our audience. And thank you so much, Josh, for answering them in so much detail. We have all learned quite a lot tonight.